Okay, let's get started with lecture number 2, and this is continuing our discussion from lecture number 1, and we're continuing to look at manufacturing process choice. So how do we find the right process for the part or product we want to manufacture? All right, that's really the basic question right there. How do we find the right process? This is the most complex issue of product design. Right, so we could make all the sketches that we want, neat sketches and really cool ideas, but unless we can figure out a way how to make it and make it efficiently and make it effectively and make it so that it functions properly, all we have is a bunch of pretty pictures. This affects how the product looks, feels, how much it will cost, and whether it can function as intended. Those are 4 of the largest, biggest, most important factors, and they're all linked to finding the right process to manufacture our parts. So this is a very detailed decision, right? It involves material variations, process options, processing parameters. It's a multifaceted optimization problem. There's that word again, optimization. Again, there's too many variables, so what we have to do is optimize it. We have to figure out what's the most important and kind of drive towards solution with that and hope that everything else kind of follows along and evaluate iteratively the whole time so that we can make sure we're not making a bad decision or we're affecting something upstream or downstream. Often there's not a clear best choice. And systematic points to guide the decision-making process include how to choose the process and when to choose the process. Okay. So we already talked about this at the beginning of lecture number 1, but product design process consists of several consecutive phases. We looked at it in the first lecture from the point of view of what decisions need to be made, but now we'll kind of look at it from a more basic framework. So the first thing is the fuzzy front end. What is the fuzzy front end? Well, that's where we're coming up with ideas, right? We're tasked with designing or solving this problem, and so this is where we're generating ideas, coming up with potential solutions or wild harebrained ideas. Once we exit the fuzzy front end, we come into conceptual design. This is where we start to make things a little bit more concrete, right? So we start to get a better feel for how we're going to achieve our design objectives. The third step here is the actual design engineering. So at this point, at the third step, we have an idea or we have a design that we think we're going to go with. Now, there's still feedback here. So, things could change depending if we reach a roadblock or, something crops up that we didn't count on before. But generally speaking, now at the design engineering stage, we're actually designing the product, okay? Working out all the bells and whistles and details here. And then finally, the last is the detailed design. This is where we're going with this design. We need to figure out how we're going to manufacture it and what everything that goes into that entails. Okay, so we can break this up into 4 phases. Phase 1, fuzzy front end. Phase 2 is the conceptual design phase. Phase 3 is the design engineering phase, and phase 4 is the detailed design phase. I do want to say that if you Google product design process or engineering design process, you will probably get 1,000 different ideas, solutions, flowcharts. So this is not the one end-all be-all production design process. This is a general one that doesn't have a lot of phases, doesn't have a lot of steps, only 4 phases in this. But it still talks about all of them are going to have basically the same fundamental components or pieces here. And again, just to reiterate, every phase involves iteration and feedback. Okay, so let's look at what happens in each one of these phases. So in phase number 1, the fuzzy front end, this is where we have a problem and we have to find a solution to it. Okay, so the design process kind of emerges organically, right? From this point, there's a lot of talking and a lot of thinking and a lot of sketching of ideas. The company may hire an external design agency to handle this design. They could join with other companies to explore a new design, or they can decide to transform a new technology into an existing product. The output of this phase, that is what we want at the end of phase number 1, is clear specifications of requirements for the product to be designed. What do we want the product to do, and how do we want it to do that? So our goal is the design problem definition. Phase number 2 is the conceptual design phase, and this is where the initial design solutions are conceived and explored. Okay, so we take what we get from step number 1 and we push it forward. So do we want to redesign a product? All right. Do we want to take a product and improve upon it, add different features, make different sizes, whatever? So we can work on the existing product working principle and the general layout, take the normal design, and then redesign it. The other option is to produce a radical design, a new design, something that hasn't been seen before. So in this case, before we had robotic vacuum cleaners, the idea of a Roomba was radical. What? You're going to design a robot that goes around and cleans the floor automatically? So this would be what we would call a new design. So we could have redesigns or new designs. So the design concept then is a design proposal that will actually work, and can be produced at an acceptable cost. Okay, so here we're not wild-eyed brainstorming anymore. Now we're really trying to come up with something that's going to work and that we can produce at a reasonable cost. So there's a lot of factors that go into that decision, and we're still a bit above the actual detailed production here. But the analysis is going to be broad, but not deep. Okay, not deep. We're not going deep yet. We choose the most promising concept from a range of options. And then that's what we go forward with to phase 3, design engineering. This is where the chosen design concept is elaborated and optimized. So from phase 1, we have our, hey, this is the thing that we're going with. Phase number 3 is to iron that out, okay? To elaborate on it and optimize it, to make it workable. So at this stage, the analysis gets narrower and deeper. This can include CAD and CAE, computer aided engineering. This is your simulation, your animations, your kinematics, all that kind of stuff. Prototyping basically means making test parts or test assemblies to see how everything functions. Validation studies and testing. Our goal here is to eliminate or minimize risks, right? So we want to do all this testing, all this prototyping, all this computer simulation so that we're not bitten later on down the road with something that isn't going to work, that we should have found out earlier. Okay. So then we move on to step number 4. Step number 4 is the last step before we get into production, and that is the detailed design. So this is where the whole design is fully detailed and documented. This is where you produce your drawings. This is where you produce your manufacturing plan, your production plan. This is where you start to formulate your marketing plan, how you're going to sell this, how you're going to market it. Any changes at this point should be related to manufacturing and marketing. All right, and they should be small. Any large changes at this point, and that's problematic. All right. In normal design, that is, when you're redesigning something, manufacturing and marketing are planned much earlier. All right, so now moving on to manufacturing choice. It's considered gradually and iteratively. Okay, so we first want to start considering our manufacturing options in phase 2, right? The conceptual design phase. So phase 1, we're not really worried about manufacturing. Maybe it pops up here and there, but really phase 2 is where we're going to start to consider what our options are for manufacturing. So for metals, we're talking about casting, forming, extrusion, forging, machining, and additive manufacturing. For plastics, we're talking about injection molding, thermoforming, resin transfer molding, and additive manufacturing. Okay, so notice it really breaks down into the first question you have to ask yourself as a designer or a design team is, are we going to make it out of metal or are we going to make it out of plastic? Okay, so that's really the first fork in the road, is the metals or plastics fork. Okay, so remember from a couple slides ago, normal design decisions, this is a redesign. This is something that we're, it's not revolutionary. Decisions may be carried over from previous designs. Radical designs, everything is on the table, right? We're designing something that's never been seen before. We have, let's just figure it out from scratch. And as I said, the first question that we really have to answer is, are we going to make it out of plastic or metal, or something else, right? But plastic or metal. So remember our talk about the manufacturing hierarchy, right? Principle, method, and equipment, right? We start up at the 30,000 foot level of principle, we come down a little bit lower to the method, and then we get down to ground level, and that's the actual equipment that we have on hand to produce the part. Where each of those manufacturing processes, or principles, I should say, comes into play with our design process now. So in the conceptual design phase, right, phase 2, we're going to be focusing mostly on principle, right? That's really all we have to go with. We don't have the solution or the design framed out enough so that we can start to get into method, and certainly not equipment. Maybe a little bit of method creeps in there. Once we move on to phase 3, design engineering, now, okay, the principle has already been decided, so now we have to start moving into the method. So what is the exact method that we're going to be using? And here, a little bit of equipment can maybe creep in. But when we get into phase number 4, our final phase, this is where, okay, we got to focus on the equipment, exactly how we're going to produce it, where and when. So this manufacturing choice is done in a stepwise manner. Okay, there's different steps to it. From the general, from phase 2, to specific and detailed, to phase 4. So it goes something like this. First, we want to figure out what material we want to do. Is it metal, plastic? Is it other? Then after we figure out that, which manufacturing principle are we going to follow or are we going to use? Then what's the manufacturing method? And finally, what specific manufacturing equipment are we going to use to produce this? So it may look something like this. Hey, we're going to use metal. All right. And then we ask ourselves, what type of metal? Well, aluminum alloy. Okay. What type of aluminum alloy? Well, a 5000 or 6000 series. Okay, specifically what type of aluminum 5000 series? Well, the 5054H2 or the 5054H4. Okay, so each step here, we're going from general to very specific. And each step is going to give us a more concrete look at the properties associated with that and the manufacturability and all the things that we need to know for phase 4, the detailed design. So this is kind of a graphic that helps us to understand the different materials that we have, the menu of engineering materials, so to speak. So at the top we have metals, right? Steels, cast irons, aluminum, copper, zinc, titanium. Obviously there's others. This is not an exhaustive list. Then we have on the going clockwise, we have the polymers, the plastics, right? Polyethylene, polypropylene, um, all the different polyesters, phenolics, epoxies, all that good stuff, nylons. Continuing down here, we have the elastomers or the rubbers, then glasses, ceramics, and then in the middle, we have hybrids. This is where we get to join these different major materials together to make these hybrids. Okay, so this can help you kind of understand what the menu is. This is not an exhaustive list, by the way. All right, so let's go back to our manufacturing triangle, right? Remember this, the different attributes. We have quality, function, and cost attributes, and then the sub-attributes for each one of these, the function sub-attributes, the cost sub-attributes, and the quality sub-attributes. All of these play a role in helping us to determine the manufacturing process. So there's mutual dependencies in a lot of these. So for example, part shape and materials are mutually dependent with the manufacturing process. So, you know, we have to be mindful that these have they're kind of woven or linked together. Okay, so let's have a look at some of the manufacturing process drivers, some of the main drivers that help us to make decisions about what manufacturing process we're going to need or be directed to or be limited in our choices regarding the manufacturing of the parts and the different components. The two main drivers here fall under the function attributes, and that would be part shape and materials. Part shape has to do with the complexity of the part, whether the part is a complex three-dimensional shape with features in all different directions and all different planes, or whether it's a what they would call a 2.5 dimensional part where it has two-dimensional shape, but then it's basically an extruded part. So it's what we call in the CAD world 2.5 dimensional. Those are simple shapes. Something that's flat is a simple shape, and it may be more open to different manufacturing processes versus something that is very complex. That may have to have an intricate casting. If you're using additive manufacturing, there's all kinds of new techniques that can be used in additive manufacturing to make extremely complex shapes that are that cannot be made through the more traditional methods. The other manufacturing choice or driver for the manufacturing process choice is materials. These obviously, remember, our first question is should we make the part out of plastic or out of metal, and that's a huge fork in the road. But there's all kinds of considerations that have to go based on the material. So these are the two main manufacturing process choice drivers. Production volume is also a very big driver in manufacturing process choice, whether you're going to do a high volume or low volume. High volume essentially means that you're able to put more of your investment in the tooling because you're going to be mitigating that high cost initially over a long run. And so that's where some of the economies of scale come into play. Making onesies and twosies, making custom parts is always going to be more expensive in the short term than making a large production run. Some processes are not are not aligned towards a large production run. Sand casting is not really something that can be done at the production volume that, let's say, injection molding or die casting can be. Those are two examples, both in the plastic and the metal world. For high volume production, extruding is also a high volume one. Part size is important as well. Part size meaning large parts versus small parts. Both large and small parts have special manufacturing processes that need to be evaluated or assessed. Large parts are limited in how they can be manufactured. We've seen videos in this class about large forgings. Obviously, those are very special cases and have to be done at a very limited number of shops and in a very limited number of ways. In the same way, small, nano, but not even the nano size, but just small parts have difficulty being handled. There's also considerations there on the process size. So part size, these four factors, functional attributes or function attributes, are going to be very important in your manufacturing process choice and need to be addressed early on in the design process. Next, we'll look at some tables. These are some tables that can help. I find them very useful because they really break the parts that we're trying to design. They break them down into different ways to see them. So the first table that we're looking here is based on part shape, and you can see that the shapes are broken down into, this is what I call the 2.5 dimensional shape. It's basically an extruded shape, whether it's a cylindrical shape, circular shape here, or non-circular. These are basically extruded shapes. You can see the two-dimensional shape here, and then the third dimension is basically just a uniform extrusion or a uniform height. Next, we get into the sheets. This is the traditional flat sheet, and then we have a dish shape. This would be made from like a drawing operation, maybe even a casting operation. But I think what they're trying to say here is that would be a drawing operation for sheets, and then we get the more complex three-dimensional shapes. Okay. What's nice is this table breaks it down for you. It's not an exhaustive list, but it definitely will get you going in the right direction for the manufacturing processes based on your part shape. We can also look at it in terms of part length. So we have the larger parts on the right-hand side here. Okay, we're up to 10,000 millimeters or over 100 inches versus the tolerances. And I think it's plain to see that when you start dealing with larger dimensions, then you also have larger tolerances, which may lead to, probably does, secondary processes, which we talked about earlier. That's another cost factor. Do you have secondary or tertiary manufacturing processes that are necessary? Most of these, especially the open die forging and the sand casting, which cater to large dimension parts, are going to require secondary operations. So there's a cost factor right there. Part size in terms of mass. Okay, the more massive parts, again, this should not be a surprise. Sand casting is up there, forging is up there. Notice conventional machining is pretty much right across the boards. So that's interesting. We can create nano size in terms of mass, nano size parts with conventional machining, or very large size parts. Production volume. This is we just talked about this. Some of the blow molding. This is what your plastic bottles are made out of. This is really a form of injection molding, the blow molding, injection molding here, in the low pressure casting, the die casting. All of these methods cater to the large production volumes. The smaller volumes, the onesies and twosies, the small batch sand casting, forging, electro, EDM, and even the conventional machining, it's really not set up for the super large scale manufacturing operations, mainly because of the tooling and the setup that's necessary for this, unless you're making parts that are extremely simple and easy to machine. All right, moving on to the quality attributes. So tolerances do not directly drive process choice, but they come into play for secondary operations. They also influence part cost, right? Because when you're catering to a more tighter tolerance or smaller tolerances, that's going to require using certain machines. It's also going to require certain skill levels of the operators. It also is going to be necessary to have a more stringent quality control process, because if you're asking for tighter tolerances, you're going to want to verify that those tolerances are being met. So tolerances is a secondary concern for the manufacturing process choices, especially when you're dealing with secondary operations. So in the chart here, we're looking at tolerances. On the right-hand side, these are larger tolerances, okay? So what we would call a looser manufacturing operation. Sand casting, obviously, is a very, we can't hold tight tolerances in a sand casting operation. EDM, conventional machining, are some of the more precise operations. Down on the left-hand side, we have the tighter tolerance machining. These would be what we would call secondary processes. This is the finishing operations. So machining can be done on a precision scale. Grinding, lapping, polishing, honing is in there as well. Okay, so these are our secondary operations that help us to achieve those tighter tolerances. Staying within the quality attribute realm, roughness, this can result in expensive surface treatments if we need to maintain a higher quality surface finish. In the previous slide, we looked at the different finishing operations: lapping, honing, grinding. Those are all going to achieve a higher level of, or a lower roughness rating, a higher level quality surface. Again, these are not main drivers, but they do ramp up the cost as well for our processes. Bulk defects and surface defects, these are not a strong driver for process choice, again, but we want to avoid or manage by design and processing conditions. So some charts here, a couple different ways to look at this. So on the left-hand side, we have surface finish. So notice on the x-axis across here, we have increasing levels of surface finish. So on the right-hand side, this would be a rougher surface. On the left-hand side, this is a smoother, more mirror-like surface. And then in the production time, on the y-axis. So, some of this is a bit obvious. What is interesting is the comparison between the different methods. So, for a drilling operation, we can have a rough surface, but if we want to do a tighter tolerance, a better surface, then we can also achieve that, but it's going to take more time. So notice that as we achieve a better surface finish, the time is always going up. And remember, time, it translates directly into cost. Okay, so grinding operations are all going to be more time-consuming, more costly secondary operations. On the right-hand side, our table here is going to be very similar to the tolerance table, because roughness and tolerance is the operations that are indicative of those two processes are going to be directly related to each other. Sandcasting up here is a much rougher surface versus something like injection molding, blow molding, compression molding. And then when you get down into the finishing operations, these are our secondary processes, and these are going to be a much higher quality surface finish, surface roughness. So with the quality attributes, material properties, the processing plays an important role. Okay, so if we're looking to improve the strength, ductility, and toughness, we can do that with the processing method. Okay, so taking a material, a metal, and trying to make it stronger or more ductile or more tough. There are processes that we can do to improve those material properties. Stiffness and density cannot be improved. They're relatively insensitive to the processing method. Okay, reproducibility is an important factor. Reproducibility basically says that over time, are we producing the same type of product, the same type of part, or do we have control of our manufacturing operations so that a part produced on day 1 is going to be the same as a part produced on day 500 or day 1000. This has a lot to do with the processing and the automated nature of the processing. Additive manufacturing is right now breaking out of the reproducibility problem that they have. They've introduced different methods to monitor the process so that there can be some level of assurance that a part produced on day 1 and a part produced on day 500 is going to have the same material properties. This is a very big concern. Machining is one of those processes where the reproducibility is actually very high, given that you're producing it on the same machine tool and with the same machine operator. It can vary slightly if you're changing tools, if you're changing the operator, but over a large time frame, the tooling and the operator level for machining is going to be very reproducible. Moving on to cost, part price demands strong attention during every phase of the design process, right? So that's something that you have to talk with as designers. You have to have an idea of where you want the part price to fall, whether it can be an expensive piece that you're designing, or whether you're trying to create it for a mass market. Those are obviously going to have a huge role in the manufacturing process choice. That plays into the material selection. It also plays into the tolerances that you're going to be able to achieve or use, and then also the joining and assembly methods. So to recap, then, the major influencers of the manufacturing process choice are part cost. Okay, that's the first one. Whether you're designing something for a mass market or a custom level is going to open up or restrict the world from which you choose your manufacturing process from. The other three are part shape, part material, and production volume. Okay, so we have cost attributes and function attributes. Those are the main ones. The quality attributes are secondary considerations. They're not the main drivers, or the major influencers, but they are secondary and can definitely influence each one of these to some extent. So manufacturing process choice then is not just how to choose, but when to choose. It's a ongoing process. So initially, you're going to be starting to frame things in, and then you're going to get more specific as the design process moves through. Remember that it's an iterative process, so there's always going to be changes. You have to understand that there's changes that are going to be made. There's fine tuning. There's recalibrations. The first question that you have to ask is what material you're going to use, whether it's a plastic or metal or something else, and that's the first fork in the road that's going to lead you down the different pathways. Design is not choosing a shape first and then sticking a material onto it, although there is an interdependency here. And the heart of design is discovering which combination of shape, material, and process makes sense in light of the required functionality. That's really the central point here, the central objective of the designers is to marry all those concerns and considerations together. That's why it's a challenge. A lot of times the initial sketches, the initial design that functionally looks like it would work, at least on paper, runs into problem when you have to start taking into consideration the material and the processes that are available to it. And that's where the real work with a designer dealing with these constraints comes into play. Production volume and part price also play major influencing roles. So those are all of the factors that need to be addressed. In the third video, the third lecture, we will look at a more concrete method for choosing the assembly method and the manufacturing method, and how those play a role in designing the part. Thank you.